All right, guys, so this is your lesson on the age of the universe, okay? So, as always, we are going to start off with a bell ringer. Well, it's to kind of get your brain in the right spot to kind of learn about what we're talking about today, okay? So, I do want you to take time and either write these in your notebook or you can open up a Google Doc and I want you to answer these. I want you to think about what you already know or what assumptions you've already made or anything like that. I want you to think about what you already know. Make some guesses, okay? So I want to know what your brain is already saying. So I want to go ahead and get you to start thinking about what we're going to learn today, all right? So do me a favor, go ahead and pause the video and answer those questions, or you can read through them and just kind of think like, what do I already know? What do I want to guess? So go ahead and pause the video and do that. All right, now that you've had a chance to kind of think about these questions on your own, all right? So the first one, it says, how old do you think the universe is? Okay, so really, honestly, I just wanted to get a roundabout estimate of how old you think the universe is. So I'm not really asking for a specific number. You could say thousands of years, you could say millions of years, billions of years. You could have just given a very vague, broad answer. I just want to see where your brain already was, okay? So I want you to think about how old everything is around us, like the stars, the other planets, everything. I just wanted to kind of to think about how long that stuff has been here or how long you think it's been here for, okay? The second one is, how do you think we learn about its age? We talked a ton about the space technology. You've looked at what we've done as far as going to Mars with the rovers and sending satellites to other planets. You've looked at that kind of technology. We've talked about what it means and what it looks like. So you already kind of have an idea of how we learn about the age of the universe. But today we are going to talk specifically about what data we look at and how we get that data. Okay? All right. And then number 3, do you think we know everything there is to know about the universe? Hopefully all of you said no. We have no clue. I'll go ahead and say that. We have no clue, okay? So we know very little about our universe. We know very little about our Earth that we live on. So there's no way that we know more about the rest of the universe than we do our own Earth, okay? We live here. We've spent a lot of time researching it. There are places on our Earth that we can't get to yet, and there's tons of places out in the universe that we can't get to, that we can't even see clearly enough to see what's inside some of those galaxies or what's on the surface of some of those planets that are out there. So we absolutely do not know everything there is to know about the universe. All right. Now, number 4, this is something I've asked you several times in this class. Do you think we know what we know now can change with new discoveries? Hopefully all of you know this by now. Absolutely. If there's data, if there's information out there, if there's stuff that we didn't know before that we can learn, then absolutely what we know can change with new discoveries, okay? So today we are going to talk about the age of the universe, how we know that, how we find it, what NASA does to learn about this. So we're going to dig in and talk about something really, really big and really difficult to try and learn, okay? So first thing, I do want to review some vocabulary. I know it's been a while since we talked about what these words mean exactly, so I want to go ahead and remind you what these mean, okay? A scientific theory is a well-supported explanation for phenomena. So it has data, it's got something there that tells us this could be true, okay? And scientific law is a set of facts that support a large concept and cannot be refuted. That means they cannot be proven wrong. All right. So the laws of gravity, we know if we pick up something heavy, we're standing on Earth, we pick up something heavy, we let go of it, it's going to fall back to Earth. We know that's going to happen without a shadow of a doubt because of the laws of gravity. And the laws of thermodynamics are no different. That's just talking about the transfer of heat energy. So you know if you pick up a cold drink with your warm hand, your hand is going to get cold. We know that's going to happen because of the laws of thermodynamics, okay? And we learned Newton's laws in class. We spent a whole ton of time talking about those. So hopefully you all remember Newton's laws. We know that those are going to happen as well, okay? A hypothesis is an explanation that is not yet supported by data. Okay, so a hypothesis is an educated guess. We might have done some research and learned some things about the topic, but we might not be able to prove our point yet. We've got to find data. We've got to find that information to back up our claim. Now, if we find all that information, if we find that data, we can make a conclusion. A conclusion is an explanation that is supported by data. So we have all that information behind it that proves that what we say could be right. Okay? Now, just because we make a conclusion and we can support it once does not mean that it's always going to be true. If it's always going to be true, we know it could be a scientific law. Okay? So a conclusion does not mean that it's always true. It just means that it's true in that one case. All right. So that is another thing to remember. When we're talking about science, we've got to be careful with our words, because we could say, like if you're watching a mystery movie, you could say, I have a theory. But if you don't have enough data behind it, you can't actually call it a theory in science. So a lot of the words that we use in science have a different meaning or a different feeling behind them when you use them in an everyday way. Okay? So we've got to remember that when we use these words in science, they mean something different. They mean something very specific. So we've got to be careful with these words. Okay? Now let's dig in. Okay, so what does NASA say about the age of the universe? All right, our best estimate right now, the most recent numbers that we can find, says that the universe is about 3.7 billion years old. Okay, so that's a really huge amount of time. It's a really big number, okay? I'm going to talk a little bit about what that number looks like in just a little bit. All right, according to NASA, this is accurate within 0.2 billion years. All right, so with all their data and everything they're looking at, they're saying that their margin of error is really small. But 0.2 billion years is still a really huge amount of time. So mathematically, it's a small margin of error, but when we're talking about that amount of time, it is a huge amount of time still. Okay, so keep that in mind. Now, this data comes from maps of background radiation from the WMAP satellite that is currently orbiting the sun between Earth and Mars. So it's pointed away from us. It is looking outside of our galaxy. It's deliberately looking farther out into the universe to see what's out there, and it's sending all that data back to NASA, and they're using that to give us the current best estimate for the age of the universe. All right, so just to give you a little bit more perspective on what I'm talking about when I say billions of years, all right, we're going to use something that we all know about, okay? We all know what a second feels like. We all know that there's 60 seconds in a minute and that there are 24 hours in a day, 60 minutes in an hour, and then 24 hours every day. So we're going to use that to kind of give us an idea of what this looks like when we compare it to time, okay? So 1,000 seconds is really, really short. It's 1/100th of a day. So we experience 1,000 seconds 100 times every single day, okay? So 1,000 seconds is not that much time, all right? We're good there. All right, 100,000 seconds is more than a day, okay? It's 1.25 days. So 24 hours plus a quarter more of that, okay? So, all right, so it is a day plus 6 more hours, all right? So that's not a huge amount of time either, okay? So we're all right there. And we talk about a million seconds. So this third bullet right here, when we say a million seconds, we all of a sudden go from part of a day or a day and a little bit more to 11.5 days. Okay, so that's almost 2 weeks. We're 3 days shy of 2 whole weeks. All right, so we go from 100,000 to a million. We go from a day to almost 2 weeks. All right, so keep that in mind. So we're talking about time. It makes things a little bit easier to understand if we talk about how large these numbers are. Okay, so that's what I'm trying to show you here, how big these numbers are and what they mean. All right, so a million seconds, we go from 1 day to 11.5 days, so almost 2 weeks. When we go to 100 million seconds, we go from 11 days to 3 years. So your entire time in middle school, 3 years. So we go from 11 days, almost 2 weeks, to 3 years when we go to 100 million seconds. Now, I don't know about you, but that's a huge difference. If somebody said, "Oh, we're going to ship something to you and it'll take 11 days." I might be kind of upset because 11 days is sort of long. I'm used to having Amazon Prime shipping and it getting to me in like 2 or 3 days, all right? But if somebody says, "Oh, like it'll take just a little bit longer, instead of a million, it'll be 100 million." That's 3 years. It's more than 3 years, okay? So that's a really big jump in the amount of time. So we go from 11 days to 3 whole years. Now, when we go from 100 million to 1 billion, so this last bullet, that's an even bigger jump. If somebody told you, "Oh, well, you'll get through middle school in 3 years," but then we're like, "Oh, just kidding, I made a small mistake. It's 31 years." That would be a really huge difference. That's 10 times as much, right? I'm not even 30 years old yet. That is a huge difference, okay? So going from 3 years to 30 years makes a huge difference. So going from a million to a billion makes an even bigger difference, okay? So keep that in mind when we're talking about million and billion. We're talking about a huge difference. It's not just a couple zeros. It makes a huge difference when you sit down and think about what those zeros actually mean, okay? So this is just to kind of put into perspective how big these numbers really are that we're talking about. So when we talk about the universe being 13 billion years old, we're talking about a huge amount of time. It's not just really, really big. It's almost something our brains can't wrap around because it's such a big number, okay? So that's what I'm trying to get you to think about. You need to think about how big these numbers are and what they genuinely mean for us, okay? All right, so now that we've talked about how old the universe is and some of the data that NASA uses when we talked about that satellite that's looking at the radiation in the background, we need to talk about the other stuff that NASA uses because that's not their only data, okay? So NASA also studies the oldest objects in the universe, including the stars, the planets, and the black holes. And if you can tell how old the oldest objects in the universe are, we get a better idea of how old the universe is itself, okay? So it's kind of like if somebody were to come to tour AJ or tour the middle school, they wouldn't want to talk to the sixth graders that have just started middle school. They only have a semester in middle school. They won't want to talk to them and ask them what middle school was like. They'd want to talk to the eighth graders who have been here almost 3 years, okay? So they'd want to talk to the people that have been here longer because they could tell them more about what this school is like. And it's the same thing when we look at the universe. We want to talk to the objects. We want to learn about the objects that have been here longer so we can learn more about it because they have more information than the newer objects, okay? Now, when we talk about these different kinds of objects, most of this information comes from stars. They're a little bit easier to study, especially when they're farther away from us, but we do study the other objects as well, okay? They also are measuring the expansion of the universe and the changes in that rate of expansion, okay? So we know that the universe is constantly getting bigger and bigger and bigger and bigger, all right? We know it's expanding. So we're measuring that expansion. We're measuring how far things are traveling, how fast they're traveling away from each other, and we can learn about where they started. So if you can tell what direction something is moving, if you're walking away from me, I know that where you are right now is farther from me than where you started. So I might not know if you started next to me or not if I wasn't paying attention, but if I know where you are and what way you're moving currently, I can have an idea of where you started. Okay, so it's the same way with things in the universe. If we know that they're moving away from us, we can tell that they were closer before. We know that everything is expanding, everything is getting bigger. All right, and we measure that, and that helps give us an idea of how long these objects have been moving, how far they've moved, all that fun stuff. So that helps us learn a little bit about how old the universe is still. Now, when we talk about measuring these, there's two different ways two of the most common ways when we're trying to measure these things. We use what's called parallax. So parallax is the use of geometry to measure the distance and size of objects that are far away from us, okay? And this is a really, really old way of measuring it, but it's very accurate because you're not relying on guesses or this could be where it's at. You're using geometry, you're using math to figure out how far away they are from us, okay? So you'll get into this math later on when you're in high school, but you're using trigonometry. Okay, so trigonometry is part of geometry, so you're using that to figure out how far things are away from us. And if we know how far away it is, we can tell you how big it is too. So they're using that same mathematical idea to figure out how far things are from us and how big they are. So the first time that we see in history that somebody used parallax was in 189 BC. Okay, so this is a fairly old way of measuring, but it works because it's based on math. We're not guessing at this stuff. We're using math to give a concrete number so we know how far away it is. Now, because things are expanding, that number will change. Things are moving, so we know that number can change. All right. The next one we use is redshift. All right. This is used to tell how a star is moving. So we can tell if it's moving away from us or moving closer to us, or if it's moving in a circle, if it's moving in an orbit around something, we can tell that sometimes it'll move farther from us and sometimes it moves closer to us. Now, I want you to think back to our waves unit before I explain the rest of this. We talked about the colors. We said that the wavelength of that light determined the color that we see. Okay? Now, light travels really, really super fast. And I want you to think about if you've got people running in a line. Okay? If that person at the front starts to run a little bit faster, the people behind them could try and catch up, so they're going to be spread farther apart from each other, okay? So when those people spread farther apart, they're giving a little bit more space between, so that would increase the size of the wave. So if we're talking about those people representing a wave, if they spread out just a little bit because that first person runs faster, they'll actually spread that out, okay? So if something is moving away from us, it'll spread out a little bit, kind of like those people that are running in a line when somebody gets faster at the beginning. So when that light stretches out, that wave gets a little bit longer, that wavelength gets longer, it'll look more red. So if it's moving away from us, it'll look more red than it actually is, okay? So it's a very slight shift in the color of light that we'll see from that star, all right? Now, if something is moving closer to us, if we use our example of people running in a line again, if that person at the front of the line, instead of speeding up, decides to slow down all of a sudden, the people behind them have to slow down too. But they're going to get closer to each other. They might even run into each other. So if we think about that the same way with that wave kind of crunching in on itself, if it's moving closer to us and it's getting crunched in together, it's going to look more blue because that blue wavelength is a really short wavelength. So we are saying that if it moves closer to us, it's going to look more blue because that light gets kind of squashed together when it's moving closer to us. And if it's moving farther away, it's going to stretch that light out just a little bit, kind of like that line of people when they start running faster. They're going to stretch out a little bit. It's going to look more red because red light is a longer wavelength kind of light, okay? So that helps us understand what direction the stars are moving. And if we know what direction it's moving, we can kind of tell how far it's moving, and we can measure the speed, how it's moving, and all that stuff, and we can use parallax to figure out those distances as well, okay? So one more thing about redshift, this is what makes stars appear to twinkle in the night sky. So when a star looks like it's changing just a little bit, you can see it twinkle ever so slightly. That's actually redshift that you're seeing. You're seeing that star spin in a really fast circle. Okay, so that's what makes those stars look twinkly and makes them look really, really pretty. All right, so now when we talk about the age of the universe, we've got to talk about some of the ideas of how the universe could have begun. Now, remember back to that first slide where we talked about what a scientific theory is. It is supported by data, but it's not definitively absolutely true. Okay, so this is the Big Bang Theory, and right now this is the most popular and the most well-accepted idea of how the universe could have begun. But again, it is a theory, so keep that in mind, all right? So the Big Bang Theory says that our universe began with a singularity and a huge burst of expansion. So really quickly, I want to tell you what a singularity is, and then we'll talk about what happened after, all right? So a singularity is a point in space and time where known laws of physics and time do not function like they do normally. Now, normally means like what they would feel like here on Earth. So when we talked about the laws of physics already, we know if we pick up something on Earth, if we let go of it, it's going to fall down back to the Earth. It's going to fall to the ground. But at a singularity, those laws of physics don't work. So if you let go of it, it might fly off into outer space or it might float. So a singularity is a really strange point, and it's a similar idea to a black hole. So the laws of physics don't really apply super well at a black hole either. All right, so a singularity is a point in space and time where those known laws of physics and time do not function like they're supposed to. Okay? All right, so that Big Bang Theory says that our universe began with a singularity. It began with a point where things didn't quite work right. They didn't work the way they were supposed to, the way they do right now. Okay? And then after that, there was a huge burst of expansion. Everything started coming together. Okay? All right, so if we look at this right here, this is one of NASA's kind of diagrams to explain the idea. All right, so right here would be that singularity, and then things started to expand, and we have planets and stars and galaxies, and then we get closer to what we consider current day. All right, now just to kind of wrap this up, remember that when we talk about things in science, we don't know everything. All right, so there are plenty of alternative theories of how the universe began, and they are theories because we can't pinpoint and say exactly definitively, this is exactly what happened. And I'll go ahead out on a limb and say, I'm not sure that we'll ever know. We could. That would be absolutely amazing to know how things actually started, what actually happened. But scientifically, they're all theories because we cannot nail down and say, this is definitively what happened. We know this is how it happened. We can't do that yet. All right. So they're all theories right now. They're supported ideas that show us this could have been how our universe started. All right. And if you do want to dig in and research on your own, go for it. I would love for you to learn about all the data and information, everything that's out there. And that would be amazing. If you can't find what you're looking for, or if you want to learn more about some of these other theories, please reach out and I'll help you find it. Okay. If you are intrigued by any of this or think it's really neat or fun, I will help you find more information on it. All right. So keep that in mind. I am here. I would absolutely love to help you learn more. All right. Now, lastly, remember, science is all about learning the information that's out in the world. We learn new things every single day. So there's scientific discoveries that they don't mention on the news sometimes. Sometimes it's something so small, but eventually later on down the road, it'll make a huge difference for us. We might not understand all of it yet. Okay. So some of the times when we learn something new, we learn that we were wrong before. Okay. So even if we're continually learning and growing, we might figure out, hey, I was wrong before, but now I know something new and I can say better. I can do better. All right. So keep that in mind, guys. Keep in mind that science is always changing. We're learning all this data. We're learning new information. Sometimes we learn something and think, oh, well, I was wrong before, but then they learn something new afterwards and go, wait, that first idea was actually right. We just need to add more information to it. Okay. So we talked about this at the beginning of the year. And I just want to make sure that we remember that science is constantly changing. We're constantly learning new things that are helping us, that are making us, we can do things better. We can fix more problems that we've got. Okay. So please keep that in mind, guys. We're always learning new stuff.